Okay. One brief announcement before I introduce the speaker. So we're going to be taking Amr to dinner after the talk, maybe just before 6 p.m. So if you're interested in joining, please let me know. Okay, so without further ado, we're very happy to have Amr, who's going to tell us about off-shell string amplitudes and black hole entropy. Take it away, Amr.
Thank you. Thank you for the invitation, opportunity to talk here. So this is this work is based on two upcoming papers with Aaron Hall. Papers should be on the time soon. Originally, it was one paper, but then we decided to split it into two based on feedback and comments, so we can get it from people. So as Ahmed just said, this is off-shell strings. That's maybe the first part. The thing is black hole entropy, which is like sort of an application of what this is. So off-shell strings. What do I mean by off-shell? So we all learn in string theory that if I have a CFD on the worldsheet with central charge equals 0, this defines for me a string background. What we're talking about here is that if I deform the CFD, so the CFD plus deformations, then this does not correspond. The string background is also not, so this gives me string background plus something else. That's in a very basic way what we mean by off-shell. Because basically, now on the worldsheet, what I have is a quantum field theory, not a CFD. So the central charge is not 0. In other words, central charge is not 0. That's one way of saying it. Another way of saying it is that the trace of the stress energy tensor is not 0. A third equivalent way of saying the same thing is that the beta functions of my fields, which are denoted by I, like the dilaton, gravitons, are not 0. These are basically three different ways of saying the same thing, that on the worldsheet, I do not have a 0 central charge CFD. How do I deal with that? Well, how do I make sense of that? How do I make sense of strings? We usually quantize strings in some background. So for example, if I don't have any fluxes, let's say I just have the Ricci scalar of an Einstein-Hilbert action, then we know that there is the string background, for example, would be something like R nu equals 0. So I have a Ricci flat manifold. For example, I don't have any fluxes, right? That will be the condition for Ricci flat manifold. Suppose I tell you I want a cone in target space, a conical singularity in target space. Well, the tip of the cone, R nu is not 0. So suppose I would like to describe strings propagating in such background, or de Sitter, or something else. How do I describe strings? How do I compute path integrals from the worldsheet? What do I do? What is the equivalent of the Polyakov action, right? What we learn is that we start from the Polyakov action, right? So if I start, say, the Polyakov path integral, I do my dx, I do my Cg, and here I have some action, some Lagrangian function of fields, and I compute the Polyakov action. I fix the gauge, and then I integrate over dx, say the ghosts, anti-ghosts, and if I have moduli, today I'll be focusing on genus 0, I'll tell you why in a second.
Sorry, I probably am very naive, but there is a natural answer for that. That is just deal with the Liouville factor.
Yeah, so good. That's it. That's exactly. I'll get to that in a moment. The Liouville factor is key here, which is a conformal mode. exactly of the metric if I fix the metric. So I'll get to that in a second. Right? So how do I deal with that? But in general, there will be, as I will explain later in the talk, there will be more off-shell junk propagating when you go off-shell, like even that global metric, and there's more stuff that we want to make sense of, and such that when I go back on shell, I take the on-shell limit, I go back on shell, I have physical results, and I'll make sense of that in a moment.
So sorry. So what are the observables you're trying to compute here?
So they're going to be correlation functions.
But
Correlation functions of off-shell insertions. So we'll
which is not something, because that's somewhat different notion of on-shell. But usually we expect that we can only calculate some things like amplitudes or boundaries.
Right.
Correlators.
Good.
So
that now we're talking about. We're not talking about holography. Okay. So this is yeah.
But even if you are not doing holography, also guesses that this is a different. It's a particular acception of.
Because it's a gravitational series, so we only expect
Exactly.
asymptotic observables.
But we can exactly. So here we're going to be. We'll be talking in a second. But we'll be computing correlation functions of shell, just like very much like quantum field theory, right? And then how do you get the S matrix limit from the correlation functions? You do something like L is Z, right? Something like that for L is Z theorem, and you get the S matrix limit, right? Something like that. To get on shell, you truncate the external legs, and you get them on shell, right? So here off shell, what we will be computing is something is correlation functions, and then there's some prescription which I will talk about today, which is basically the prescription that tells you how to go from on shell to off shell, and make sense of what off shell theory. And these prescriptions, just want to give you an overview of what the problem is.
Sorry, before going there, so
Yeah.
there's a whole formalism that tells us how to go off shell. It's a string field theory.
String field theory is second quantized. This will be first quantized string theory, and I'll tell you why it's easier to compute in what I'm going to tell you. It's
But in
easier to
principle, the observable you want to formulate has a.
it's related to in a very, and we are in our paper we actually make connections to string field theory all the time. And let's see, that's a good question. So let's make sense of this. Here I was talking about Polyakov action, but now let's focus for now on the sphere. In the 1980s, you are in the context of, which is not exactly what I'm going to constrain myself with, in the context of nonlinear sigma model, Arkady Tseytlin, just to be specific, proposed a specific way of going off shell, computing off shell nonlinear sigma model. And this is true at all genus, but specifically on the sphere, genus 0, things are subtle. Why is it subtle? Because if this was the sphere partition function, suppose this is a sphere, then what I have here is this guy sitting down here. And this guy on the sphere is the SL2C. SL2C is non-compact. So what we do is we say on shell, Polchinski, that what we do is the SL2C has 6 real parameters, the global conformal transformation, L-1, L0, L+1, and what we do is on the sphere, we fix 3 points, right? Z1, Z2, and Z3. And we compute the 3-point function and 4-point function and so on, but we never compute, let's say that this is the amplitude of genus 0 with 0 insertions, A01, 1 insertion, this is the genus, this is the amplitude, and A02 is equal to 0. You agree?
So do you mean this is the amplitude?
Yeah, so the sphere
this is only true for Poincare invariance background.
which is what we mean by actually on shell backgrounds here, string backgrounds. On shell.
No, but for instance, consider like Liouville theory, for example, has a 2-point function on the sphere that is non-vanishing, and you can think of that as a string background. And the reason is that because of the Liouville wall, breaks function invariant?
This is a non-critical string. So good. So non-critical, that's non-critical string theory because of the linear dilettante, right? What we can also even think of non-critical string theory as critical string theory in a different background. That's true. So I will just start by critical string theory and then I'll comment on non-critical string theory just to make sure what you're saying is right. What we conclude is that the amplitude of a sphere with 0 insertions and 1 insertion and 2 insertions is 0. Does anybody agree with that? Yeah.
Just to be clear, so you treat adding a relevant operator or a marginally relevant operator on the same way as being non-critical string, or you want to distinguish between them? Because both are off shell. If I have a non-critical string theory, I'm off shell. And if
why do you have a non-critical string theory off shell?
Well, if I don't complete the central charge back to 0, it's off shell. So
well, but if you compute the beta functions of the dilettante, right, critically, I mean, actually compute it, you will find it's 0. Of course, there's a contribution from the stress energy tensor. And so, but we never consider non-critical string theory off shell. Okay. I mean, in the sense that I have a quantum field theory. That's why I wanted to comment on I want to leave out the conical theory for a moment. And focus on critical string theory.
Which have relevant and marginally relevant operators?
Yes, I will comment on that. I will comment what I mean exactly by off-shell. By off-shell, I mean, well, I think I said that already, mean that my insertions on the worldsheet will not be Weyl invariant, right? Because that's a condition, right? We say that we have L0 acting on epsilon. That's what we mean is that we have 1, 1 insertions, marginal deformations. But if I have relevant and irrelevant deformations, any non-1 deformations, I have an off-shell insertion, and that's why I break Weyl invariance.
Sorry, but in context of what you said in the
Sure.
beginning, I'm confused. I don't see the difference between critical and non-critical. Non-critical is just that you have like some different CFT, right? You have extra. So why are distinguishing these two cases in your language?
I'll come to that. Let's just. There's a subtlety there. There's a subtlety there. Okay. So if I may just continue, I know the question. So just yeah. There's a little bit of a subtlety that deals with the conformal frame. Okay. So how I deal with the conformal frame off shell. That's exactly what the subtlety is. Anyway. So does everybody agree with this? That this is true on shell.
I'm not trying to understand that. Isn't it related to how you regularize the volume of the surface?
That's exactly, that's the next point, which is the Lewin-Polchinski paper. That's exactly true.
So why is it 0?
It is 0 because I don't have, because of the SL2C. SL2C is a non-compact group. It is sitting right here.
Why would you say that it diverges?
What's that?
Why would you say that it diverges? Oh, I see. Okay. No.
I haven't put a cutoff yet. I didn't put a cutoff on the sphere yet. I didn't do anything. That's what we learned. We say we have an informal, we have a non-compact group sitting down in the denominator, and the next thing we say it's infinite, and therefore if I denote this factor by k0 over infinity, I conclude that this by 0. That's a very basic standard statement in on-shell string theory. Okay, that's basic standards. And this means what? This means basically I don't have any tadpoles, no one-point functions of operators, and here I don't have a tree-level mesh shift. That result has been known for since the 80s. But remember that before I skip the step here, when I do Faddeev-Popov, of course, here before I actually have the conformal invariance, I have the diff cross Weyl. I fix the diff, I fix the Weyl, and I'm left with the conformal Killing group, which is SL2C on this, right? Okay. But what if my worldsheet theory now?
Actually, it's over C2. No?
Yes, SL2C.
Over C2.
Over C2?
Yeah, it's PS over C2.
Yes. Yes, be correct. But now, what if I don't have Weyl invariance on the worldsheet? This basically means I have a Weyl anomaly. Right? So if I have a Weyl anomaly, how do I fix the, cannot really fix the diff and vial and get the SL2C, because the SL2C is the remnant, the residual global gauge transformations that live in both vial and diff. But if I don't have vial to start with, because I have an anomaly, then how do I deal with this guy? And how do I make this non-zero option? How do I make sense of that? Okay, that's the question. That's basically where this is heading, right? And this SL2C has been the volume of the SL2C has been recently the subject of several debates. How do I deal with this guy, for example, versus the SL2R? And then I get to a very critical paper by Liu and Polchinski, really nice paper, 1987. Liking on the title, but here's the question they asked. They say on shell, basically this is true. This is the first statement they start with. On shell, the sphere with 0 insertions, 1 insertion, 2 insertions are 0. Okay, because I have conformal invariance. But I break vial invariance, conformal invariance, then how do I deal with that? And the reason is the non-compact nature of this SL2C. So they asked the question, how can I understand this with a UV cutoff epsilon on the world sheet? Let me on the SL2C. Back to your question that you asked. Now let me regularize the SL2C. That's the question they asked. How do I understand the divergences coming from here? And here is the, I'll give you the punchline. I'm not going to put the calculation, but the punchline is the following. Is that I can understand that the UV cutoff of the SL2C can be understood as the limit of 2 and 3 vertex operator insertions colliding on the world sheet. In other words, if I compute any amplitude, but now suppose I integrate over all insertions, I don't fix 3 points. What is the standard way of dealing with this? The standard way of dealing with this in Polchinski is say fix 3 points, Z1, Z2, 1, 0, and infinity, and we deal with it. We're good. But here they say the following. That's the observation. That's which is really nice. Is that if you integrate over all insertions, so dZn of whatever quantity you compute here, the limit and take the limit of 2 and 3 points colliding, you will get a volume, a logarithmic divergence or some divergence that is actually the volume of the SL2C. So you can cancel the divergent volume of the SL2C against 2 or 3 points colliding on the world sheet. In other words, they gave it a dynamical nature. And that's key to what we're going to actually discuss here. That's a key observation of. In other words, they said the following. They computed, so let me get you the other, I'll put it here. They made 2 observations, key observations. They'll be a beautiful paper. That the volume of SL2C, just compute the volume of SL2C in any way you like, has the following nature. Well, we're going to put this because I'm not going to remember the coefficients. It has a quadratic divergence and it has a log divergence. So just compute this guy with an epsilon. What you'll have is a quadratic divergence and a log divergence. This quadratic divergence comes from, if you were to compute any amplitude, the calculation is in the paper, it's there. If you were to compute any endpoint amplitude, take the cations, for example, and take the limit as 2 points colliding, and 3 points colliding, you will get log divergence from 2 points colliding and 3 points colliding on the sphere, and you'll get quadratic divergence from 2 points colliding on the sphere.
This is in the context of calculating on-shell quantities with large number of vertex operators, right?
Yes, good, exactly. I was going to comment on that just exactly. Even if you do this for on-shell, so even if you do this for on-shell, and off-shell will be true, that is going to be the case. So if you actually compute, let's say, let's say the, so Polchinski said, before I digress, Polchinski said, okay, well, we can work in an RG scheme, any RG scheme. I can cancel the quadratic divergence, but I'm left with something here, some coefficient. And logarithmic divergences are universal in nature. You cannot really bury them under the rug, as you can do with in RG with quadratic divergences. So he concluded that the SL2C volume will make the sphere vanish, the sphere function, sphere partition function. So that was the conclusion. Versus, for example, the SL2R, where you only have linear divergence, but you don't have a log divergence. Okay. The second observation. What I'm going to put it in equations, he said it in words. Suppose I compute the K means correlation functions of n insertions on shell for now. Let's just 1, 1. Just start with 1, 1. Let's just go through this exercise, right? 1, 1. And then I take the limit, but I integrate over all insertions. So dz1, dz2, dz3, dzn. What you're going to get is the following. E minus 2 plus log epsilon times the amplitude with 3-point fixed. So you're going to factorize the n-point correlation function with all points integrated on this guy. This times that. This is true. This is true calculation. Done it several times. And Polchinski actually, the worst for him to actually take note of it in his paper.
Is there an argument that the log is not multiplied by any power of epsilon?
The log is not multiplied by any power of epsilon. So we have, you mean terms
the
like
log
this?
divergence the log epsilon just comes along. Like when you shift epsilon, you don't get anything dependent on epsilon.
Yes, you don't get so good point. You will notice that on the sphere, not on the plane, this is true. But if you do it on the plane, there is such a term. And that's a good point. So on the sphere, it's only these that actually appear. But now here is the point. Well, here's the point. Let me put that here. So this is what Polchinski and Liu basically noted, is that you can factorize any endpoint amplitude on the Mobius. They call this the Mobius divergence or Mobius group, Mobius divergence. Okay, good. So far so good. I haven't really got into any.
What is the value of the constant?
They mean that
Just 1?
These?
Yeah.
Some here it was like pi cubed.
But my question is, the constant does not depend on the theory, or like this A?
It will depend on the theory.
Okay.
It will depend on the theory.
On the chart, right?
Yes.
Okay.
It will depend on the theory. That's what you mean. It will depend on the theory. Here, of course. So yeah. So we know the problem. What the sphere partition function, why is it problematic? Why does it vanish off shell? On shell, and the problem is the SL2C. I mean, that's basically the message. Is this point clear?
On shell, it's not a problem. It's a feature, right? So.
And on shell is 0.
Right. Yes,
Exactly. But if I want to compute something like this, and I get so I can jump digress for 1 minute to give you a note for this, because this is what the main motivation, but then I'll come back. Suppose I want to make sense, and this is the second part of our paper. So I want to make sense of this guy, of the S in string theory.
So what is the second entry?
S out,
Meaning
meaning the quantum entanglement, the one loop correction to this guy. Right? This is tree level, this is quantum level. Suppose I want to compute this guy in string theory. Right? This is tree level. These are quantum corrections. Right? So if I want to compute entanglement entropy of the black hole entropy, but I want to compute this in string theory. Tree level means what? Means G equals 0, correct? Suppose I want to do this. Yeah. 1 minus beta del beta of my Z sphere. Suppose I want to do this. How can you do it? Well, this guy is on 0 on shell. And this is the first variation, right? First beta variation. So 1 point function, 0 point function, but they vanish on shell. It's an application. Here's the question. Well, how do I compute this if this guy's 0? Well, I have a conical singularity here. The conical singularity is a background that I just said at the tip, R mu nu is not 0. So how do I make sense of this? Do I conclude, okay, well, in string theory, there's no way I can do A over 4G. The sphere partition function does not contribute to the entropy. The sphere as a genus does not contribute to the entropy. Forget about the problem. Right? But no, that would be the wrong answer. Because in target space, if I have a cone, the tip R mu nu is not 0. And therefore, the answer is just not 0. No. Then you have to tell me how to compute this thing, this object, in a background that does not solve Einstein's equations, for example, in this case. You have to tell me what this is, how to compute it from the worldsheet, what to make sense of it, and is there a prescription, so on and so forth. But here's a direct application of that. Actually, that was the motivation, but now it goes beyond that. Because what I'm trying to tell you is that how do we compute in perturbative string theory off shell? In general backgrounds, because it doesn't have to be a conical singularity. It could be anything. Okay? But that's just to give you a flavor of why this is needed. Okay? Any questions so far? No. So is the motivation clear? What's going on? Everybody's happy? Okay, let me move on. Okay. So
well, maybe I'm not yet so happy. So
Sure.
can you in the example you took, you had a very singular situation with the cone.
yeah.
On there, yes, you have a horizon and you have a singularity inside the black hole, but do you imply?
I have a Euclidean Rindler space for now.
Okay.
Okay. So this application I had in mind is, well, which I was going to talk about later, is Euclidean for now, Rindler.
So what is analogous thing to the very singular situation you have on your left?
What do you mean by that?
You have here quite a singular background. It is 0 everywhere except at the point.
Yes,
So
it's flat space. Yes.
Yeah, so that's on the left-hand side. Do you have on the right-hand side something similar, or I'm trying to see what is analogy?
Oh, I'm not sure. What do you mean right-hand side, left-hand side? I have a.
You have an A over 4G.
Yeah.
For example.
Yeah.
Is that related to something singular?
I think when you take the derivative with respect to beta,
Uh-huh.
you're considering a slightly off-shell.
Yeah, of course, because when you take the beta variation, you take the beta variation of something like slightly off-shell background already. I mean, it's a one-point function because it's going to be like a generating functional, and this you take a one-point function, it's going to be a one-point function, which is not zero. So this is just a simple one-point function. But if I have a flat space and this guy is zero, I think, right? Then I conclude that the entire entropy is zero. But this is not zero because at the tip it's not zero. So I have to make sense of how to deal with that. So that's basically what I'm trying to say. That's what we mean by go off shell. And there's lots of backgrounds that are in string theory that are off shell. If you want to make sense of like ER equals EPR in string theory, then we have to go off shell.
Very naive. So this is, I agree with this when the fact that the 0-point function is zero in string theory per units of volume, because
I mean the way.
Per units of volume, because
Uh-huh.
I give you an example. Consider the two-dimensional black hole, SL2C over U1. Let's mean with it. There, the partition function C0 is non-zero, and this is off shell, well-behaved string theory.
It is not on shell, but it's not zero because it's off shell. It's not zero because of the boundary term. No. It's SL2R mod G1 is a non-compact Wess-Domino-Witten model.
It's a gauge.
It's a gauge Wess-Domino-Witten model, and it's non-compact because there is a boundary term. So hold on a second. So what I'm trying to say, it's perfectly on shell, but the sphere partition function has a bulk term and has a boundary term.
What is SP? So
Sphere, so I sphere, the action of the sphere, has a bulk term, which is zero on shell, but has a boundary term, which I haven't yet talked about, which is the reason why. For example, in SL2R module 1, there's a very good example of this particular cigar, or ADS3, because it's the gauging, is a boundary term. The boundary term is what I haven't talked to you about yet, right? Then what is the boundary term? And let me answer. That's a very good. Suppose I write this. What is the reason? Suppose I write this. ddx e to the minus 2 phi, all convenient to there's a boundary term. But this is the reason why it's not. That's off shell, it's a boundary term. And I have here some Lagrangian, which is function of this del phi I. Del phi I meaning all the fields here. Why does this vanish when I take the derivative with respect to phi? When I take the derivative with respect to phi, and this is a known fact of the sphere partition function. You can see it even within the last paper. If you take the derivative of respect to phi, it is proportional to the equations of motion. Is this clear? Why? Because it is only the dilettante is sitting right here. Does not depend on the derivative, right? The only inside the Lagrangian, there is no dilettante. All the factors inside the Lagrangian are derivatives of the dilettante. The only factor that has no derivatives on the dilettante sitting out here. So it's a fact that if you take the derivative with respect to the dilettante, you get something which is proportional to the equations of motion, and you get zero. This fact in target space is related to, on the world sheet, the non-compactness of the SL2C. In fact, I can write down the boundary term for you. Right? This is the fact about sphere partition function, but
where is it important here that it's sphere?
this is the classical action. So this is R. Suppose this is R plus something like this. No fluxes, and Let me write down that just a minute. Let me write down the boundary term before I digress.
But just this fact that it vanishes.
So what is the boundary term? Just suppose I write it. This is the classical action. So I meant in. Just let me write it down for you completely. So I have 4 del phi plus r.
Oh, this is target space actually.
Right, target space. Yeah, target space action. Right. So what do I get? I get that minus 2 e to the minus 2 phi, correct? Times the Lagrangian can be written as this. E to the minus 2 phi times del L by del phi. That's how you get the given talking boundary term in string theory. That's why it vanishes. Then you can say, okay, what is the boundary term? There's going to be something like, that's a fact. So the statement is the following. The classical action of string theory, which is a sphere, is a boundary term. Point is, I don't know, nobody knows, I guess, how to derive the ADM mass, or the given talking like boundary term, from the worldsheet. It's just an open question. But what we can do is derive this. And we derive this in our paper completely. So we start from a sigma model with general backgrounds, completely off shell, and at the end of a very, very long calculation, 5-6 page, I'll give you that action. So I start from some sigma model, I'll give you that action. Using Tseytlin's prescription, which I didn't talk about much, because this is at the heart of what we're doing in the paper. But this is to answer a question. The SL2R module 1 is a cigar, and a cigar, the bulk function vanishes on shell, and the reason it doesn't vanish, the sphere, is because of the boundary term, not because it's off shell. Just to be clear. Okay. Now suppose I want to start. Can I? Well, this will. Yeah.
There's another one. Can you push?
Well, good. Okay. Now I want to get a bit more. If everybody's comfortable so far, or is it too? I haven't said anything about my work yet. Which is fine. That's fine. It's fine. Perfectly okay. I just want everybody to be happy with what I'm trying to say.
Usually everyone wants this in the world.
No. Happy here. Because usually what I do is that I get into the details right away and like nobody's happy. So let's just take it slowly, step by step. So far, haven't yet talked about Tseytlin prescription. So Tseytlin prescription has 2. Let me write it down. We call them in paper T1. We call them T2. It tells the following. The partition function Z0 equals, going to write this and then I'm going to explain it, del by del log of epsilon of my partition function. So this would be the classical, let me write it here, even the classical action in target space is related to the partition function that you compute from the worldsheet by this formula. Does that make sense? At least that's what he proposed and tested to some orders of alpha prime. And he has another one where it is del 1 plus this does something, this is something else. Let's focus on this one.
Is it supposed to be equal or
equal. What it says is the following. Compute this on the worldsheet. So I give you some sigma model, let's say. It doesn't have to be a sigma model. Let's assume it's a sigma model. For some massless amplitudes, not massive. Massive is tricky. Also too massive. So suppose I give you something like this. Suppose I give you an action. I'm using I0 for the target space. Suppose I give you a worldsheet action that looks like this. And some dilaton and some Ricci scalar on the worldsheet, plus maybe b mu nu fields.
You're talking about partition functions. What is massless versus massive?
Yeah, this is massless fields for closed strings. The dilaton and the gravitation, right? For massive, it's non-local, and so let's focus on the massless fields for now.
Even the background is still not on the
Yes, that's exactly right. So suppose I give you something like this. Again, I'm not confining myself in our paper to nonlinear sigma model. We could be deforming around any conformal field theory, strongly coupled, doesn't have to be even geometric background. But let's suppose here, I'm deforming around flat space, right? You know, this is deformation of flat space. Because I can represent G mu as eta mu plus H mu somewhere. Suppose I give you this. And I want you to compute the path integral. What do you get? Just a practical, it doesn't do the formalism. There's a formalism and there's the application. So suppose I gave you something like this. And I ask you to compute the path integral of this guy. Well, I'm going to put something here because this is necessary. This is target space. So where's I can compute this object? What do you expect to get? Well, what I promise you will get if you do it right, using heap kernel, least regularization, with a UV cutoff, handling several subtleties in the right way, what I promise you will get is this. It's just give you an application, a flavor, but with this prescription. I think there's a factor of 1/2, I think maybe 4, and higher alpha prime corrections, at least the first order of alpha prime. And this log epsilon, you could say, this is the partition function in the worldsheet. I need to subtract the logarithmic divergence, but the logarithmic divergence here, I could maybe subtract or divide. What ends up being correct is that I divide. There's a factor here related to d minus 26 sitting up here. So I do del by the log epsilon, and I get of this calculation, I call it K0. And I get my target space action. This guy. It's a long calculation, but it will show you the point. And this thing, this object log epsilon, if you remember, is exactly related to the logarithmic divergence of the SL2C. And remember,
but is it automatic? Because that's outshell amplitudes and this effective action that generates exactly those outshell amplitudes.
Yeah,
So it should have been that way, right?
Yes, exactly. That's exactly right. And that's the power of this observation. And the log app. So here's an exercise. You could do that. Take three graviton on-shell vertex operators. On-shell gravitons. We know what the vertex operators are on-shell. Compute the 3-point function, 3-point amplitude. Integrate over all vertex insertions with a UV cutoff on the worldsheet. Do that. You'll get this. That's another way of proving that this is right. Because what is R? What is the Ricci scalar? Where does the Ricci scalar come from? The Ricci scalar is proportional to this V graviton 1, VG2, VG3. So take on-shell vertex operators of a graviton, compute, put a cutoff, integrate over all insertions. You'll get exactly the same thing. Okay? Because the Ricci scalar comes from there. Okay. So now, why the del by the log epsilon? Let me write down 2 things before I end. I'm going to do this a lot more. Keep talking. Depends on how bored you are. But... Okay, I want to make 2 points. What is so special about the derivative, not the division? That's one. And I haven't written for you so far the sphere partition function. So let me write it down. This is what it looks like in target space. But let me write it down for you explicitly. Now, I'm going to use RG language now. RG on the worldsheet. Okay? I'm going to use RG on the worldsheet. So I have a worldsheet theory. This worldsheet is not a CFT, it's a Q of T. Because it's a CFT plus some deformations, the deformations could be anything, so it flows, right? This flow. Now I'm going to treat log epsilon. I'm going to define it as T, and I'm going to call this RG mu, RG time. This RG scale, RG time, or RG scale. So here, at the core of what I'm trying to say, is RG, renormalization group. Okay. Now, familiar with the Callan-semantic equation? I'm going to write it down, but it's going to be something like local Callan-semantic equation because it's a sigma model, in the sense that the coupling are position dependent. It's usually not the case. So what is this? What does this mean? It tells me the following. D of my partition function by D log T is del by del T plus the beta functions of my couplings, del by del the couplings. I do not, couplings, phi here is not the dilettante, phi could be G, U, B, anything, just it's a generic symbol for that, acting on equals 0. That's the renormalizability condition of the Callan-semantic equation. Let me even put it somewhere else. I'll put it here. Can I? Because I've motivated how to get this from the target space, but I haven't said anything how to get it from the worldsheet in a methodical, systematic way. So suppose now this is the partition function, genus 0 partition function of some sigma model, some Q of T, some quantum field here. Doesn't have to be a sigma model again. And this is RG time. the derivative beta I del by del phi. This is the Canon's equation. From this, I get that this is equal to that. So I get what? I get that, call this I. Get that del by del log epsilon of my k0 equal to beta I and I call this my action. So I compute this guy. This can be computed. Or, yeah, the partition function, off-shell partition function of some theory on the worldsheet. This is not now on-shell or off-shell, completely off-shell. So this means that your CFT has been deformed by whatever.
But here everything was on shell, right? So
Everything is off-shell because G mu is off-shell. It's not flat space.
Okay.
Okay. It's not flat space.
Well, that's different from being off shell.
It is off-shell. You're deforming on flat space.
No,
So something arbitrary.
So it's not a CFT, right?
It's not a CFT, so it's not off-shell. Sorry, it's not on-shell because it's not a CFT. CFT, if I don't have a CFT on the worldsheet, then I'm off-shell. Is this not clear by now? If I don't have a CFT on the worldsheet, then I'm off-shell.
Just from what is written there, it's not clear that it's not CFT.
Well, G mu is what? G mu is a deformation of flat space is Polyakov. Polyakov is on-shell.
It could be the G mu is.
Yeah, but here it's arbitrary because I haven't said what it is. It's completely yes. So this is completely arbitrary at this point. I'm not saying that this is, for example, put the cigar or put ADS3. Yeah, it's a at this point. Yes, I think this one is just optional because I don't know what it is. You could tell this local background independence. I'm very agnostic to what the background is at this point. So now I compute my partition function, which is off-shell. Some CFT plus some deformations. And
the partition function, the sphere partition function is highly ambiguous because of the counter-term ambiguity. You have a non-trivial curvature on the sphere, so the K0 itself is just not physical. But presumably, you are claiming that this derivative is unambiguous.
yes, because of the SL2C, because of the SL2C factor, and the ambiguity, or you're referring to, is basically because of the SL2C factor.
I'm just talking about the fact that when we talk about sphere partition function, there are counter terms you can write.
Counter terms in holography.
No, counter terms on the worldsheet.
Okay, fine.
Also to the
Well, the worldsheet. Okay, go ahead.
And it can be multiplied by an arbitrary function of the dimensionless couplings in your theory. So it could be the coefficient when you expand out your T mu nu.
But the log divergence, the point of the Tseytlin thing, which I was going to get, is that the log divergence is universal.
That's what I was saying.
Yes, the log divergence part is universal,
Yeah.
and so it has the power. So it's just I wouldn't say the words now. It has the power of eliminating this non-ambiguous sort of quadratic divergences in this thing, and only latching on the universal behavior of the logarithmic divergence of the SL2C.
But is it correct that it depends only on UV CFT? So in that sense, it is probably on shell, right? So it's not sensitive to deformation. It's only sensitive on the UV CFT.
That's right. So I'm a little confused how you make sense of this I0 away from the CFT.
So what do you mean exactly by that?
If you have example of so suppose I talk about icing, right? Try mass deformation flow to a gap theory. What is I0? Is I0 always equal to 1/2 or something else?
It's not good. Okay. It is the reason there's an ambiguity. I think I get your question. It is going to be a number modulo some what we call in the paper gauge transform. So can I answer? I want to answer your question. Give me. I'll finish this and answer your question, okay? Because that will bring me to that question. Okay. So I'll answer this. I promise I'll come back to your question. Just give me a minute. What I was okay. Let me do this quickly. What Tseytlin pointed out is that there is a particular field redefinition. Remember that we're looking at RG, okay? So we can do field redefinitions in target space, and these are equivalent to RG schemes on the worldsheet. So that's part of the answer, part of it, not the whole thing.
Sorry, you calculated that derivative at epsilon equal to 0, or?
Yeah.
You can calculate it, yes. So at this point, you can do epsilon equal to 0 here,
No,
or
in all the formulas, it's epsilon equal to 0, right?
yeah. But yeah, that's a good question. That's a good observation. I wasn't going to mention that either, but yes. Okay. So I was okay.
But then you need to throw away this epsilon to the minus half by hand, right?
Which one?
I mean, like in the K0, there's a
Yes, there's two ways to do this. There's two ways. Yes, there's two ways to do that. In the T1, good. In the T1 prescription,
it doesn't that derivative combination of derivatives that would also cancel this.
That will cancel that.
Yeah.
That's why this is the correct prescription.
Good
observation. Thanks. Okay, that's it on time. That's exactly right. In the first one, it doesn't handle. You just throw it. You assume you work in an RG scheme or figure definition where you can actually throw it under the block. Okay, so what Tseytlin claimed or found in his papers in the 80s is that there's a particular field redefinition where K0 can be written, written as ddx square root of g e to the minus 2 phi, and he called this the generalized volume. So let me call it here, because of the e to the minus 2 phi, which is what you would expect to get if you're computing any classical action. But because of the time, I think I will have to do the following. Now, let me write down I0. I0 is going to be, because of this beta function, it's going to look like this. Some factor half beta. Let's focus on the graviton of dilaton for now. Beta E del G. This is the beta of the graviton, beta of the dilaton, phi, K0, and this is going to be integral ddy square root of g e to the minus 2 phi times that beta function. And this beta function is where the field redefinition is. You see, this is not the standard beta function. I have a twiddle up here. It's not. This is the dilaton beta function. This is the graviton beta function. This beta function is very, very special. This is where the field redefinition that I actually found, because it looks like this. Beta phi is beta g, is beta of the dilaton minus 1/4 beta g beta mu nu g mu nu. A particular direction in RG space that shows up here in beta twiddle phi, and it is beta twiddle phi that gives you this r plus the gradient of the dilaton. There's a lot here to be said, a lot about what is so special about this field redefinition. But here, notice that this is a special combination of the dilaton, very special combination in RG space of the dilaton plus the metric times g mu nu, and the action at the end of the day takes this form, and this is basically the representation on the worldsheet of the target space action if you have r plus the gradient of the dilaton.
Is this just combining like the trace part of g mu nu with the dilaton?
Yes, yes it does. In a very special way. That's the field redefinition that we basically found. And the way he justified it is by calculations, explicit calculations to like order alpha to the prime. He and others, many people verified this. Many people in the 80s and 90s, early 90s, verified this calculation to higher orders of alpha prime. But no one really understood exactly what was going on, except that it gives the results. What's going on? How do you go off shell? How do you handle the conformal frame? How do you handle things? Now let me get back to two questions. How long?
How much time do you need?
I don't know. As much as you can. I can keep talking for a while. I haven't done anything. I haven't said anything. I still have a lot. You tell me where to stop and I'll stop.
Okay, let's put a cutoff in 10.
Okay. So, what? I was going to say what? H orbits or
You said you were going to answer a few questions.
yes. Yes. The conformal frame question. So the idea here is that when we do the calculation, where's the well? Yeah, this guy here. There's two ways to handle going off shell with respect to the conformal frame. Either that you consider the conformal after you fix the diff, either that you consider this a propagating metric, a propagating field in the worldsheet. That will be the Liouville mode, the non-propagating field. Or, which is what we assume here in this formalism, you fix omega. So you actually do the partition function calculations in a particular conformal mode. So I fix it, I don't really integrate over it. It's not propagating. But I do my calculations in a particular conformal mode. But then what we show is that if you deform away from omega to like delta omega, you get a term that is proportional to the beta functions. So now the words, the question that I've been sort of delaying is that if I do my partition function, now I'm going to write my partition function or my effective action in terms of this, by del omega. Then I get my beta functions. And these are my vertex operators. By that I mean this. And so now, and this is for omega plus del omega. So infinitesimally, I compute my partition function for a specific conformal frame. For an infinitesimally neighboring conformal frame, if I do take the functional derivative of my partition function that depends on it, you're going to get an answer that is proportional to the beta functions times the expectation value of this operator. And by these two angle brackets, I mean we're not dividing by the partition function. This is a true statement. And so what I'm trying to tell you is that even if you do that, with the RG that we're just talked about, you can always find a field redefinition by which it is equivalent, your action is equivalent up to field redefinitions or RG schemes of the conformal. That is one way of, that's why we handle it. And the reason is, well, we could have handled it the other way. We could have done it the other way. But the formalism here is built on the fact that if you fix the conformal mode, do the partition function in a particular conformal mode, for a neighboring one, which is really close, the integral will give you an answer that is proportional to the beta functions. And so this is what we call field redefinitions in target space, which is something we do always in classical, in effective actions in target space. We always do field redefinitions, except that in string theory, field redefinitions will give you the beta functions, which is basically equations of motion. So these are equations of motion. That's why we handle it here. So versus the propagating Liouville mode. Now, before I get, okay. 2 points I'll mention. what Aaron and I show in the paper is the following. Is actually, instead of relying on the validity of the prescriptions by explicit calculations, as has been done, like you compute and you get consistent results, what we do is we prove it. So, when I say we prove it, we do the following. We prove it. We define two regimes of locality on the world sheet. One where we take the cutoff to 0, such that log epsilon goes to infinity. We call this the S matrix regime. I'll do it like this. S matrix regime, where epsilon goes to 0. You take the UV cutoff, it'll be really close to 0 on the world sheet. In this case, what we show is that del by del log epsilon, T1, I'll call T1, and T2 produce the S matrix. They give you the S matrix, Euclidean S matrix, not just the Euclidean S matrix, but they give you the Lagrangian S matrix. In other words, we show explicitly in the paper how the del by del log epsilon is beautifully related to the Feynman I epsilon prescription on the world sheet by Witten. This is a paper written by Witten in 2013 called the Feynman I epsilon in string theory. And it has to do if you have a world sheet near degeneration, so you have a pole, you're near a pole. What happens in the world sheet is that you degenerate. I'm not sure if right, and then you take some contouring complex space. But anyway, the story is complicated, except that we show that they're equivalent. We work out cases beautifully. It's right on the nose for S matrix.
But what does it mean for I0 when you have no insertion?
This is an on-shell insertion. This is for on-shell. This is S matrix.
Okay.
I'm calling S matrix, right?
So everything in the vertex operator.
Yes. For marginal difference. That's what I mean by S matrix. Because there is no off-shell S matrix. 2 is we take epsilon. We call this the action regime or the off-shell local action regime. This is where we construct the action. Here, epsilon is small, but not close to 0. This is the regime where we actually show that the following: if I have a CFT plus some irrelevant and relevant deformations. I'm going to write the equations now. So if I take any CFT, it doesn't have to be a sigma model. It doesn't have to be. If you compute, we show that Tseytlin prescription in conformal perturbation theory said so at all orders in conformal perturbation theory. Every order by order in perturbation theory, we show that the following is true. If I have the beta functions, if I'm sitting on a CFT, this is what I mean a CFT, and I have the equations of motion are 0, so I have a string solution. This is the easy thing. This is the easy part. The tough part, it's really tough, is to show the opposite. Is that if I have a string background, meaning the equations of motion are 0, this corresponds to CFT on the worldsheet. Because otherwise, any off-shell prescription, if I don't show you this is garbage. have to show me that when I go off shell, order by order in perturbation theory, that when the beta functions are 0, well, when I have a string solution, I have a CFT on the worldsheet, and when I have a CFT corresponds to a string solution, and a string solution corresponds to a CFT. We do this order by order in perturbation theory for deformations which are relevant, irrelevant within some constraints. So this is the proof. We show that what we do is we calculate correlation functions on the sphere. We put a cutoff, and we act with Tseytlin's prescription, right? And then we show that this is actually true. This is a very subtle way. I'm not going to get into it now. But just suffice it to say that this is really what we prove in a very rigorous manner, not really explicitly by just calculations, like already Tseytlin kind of showed. So we show that. That's one thing we show in this regime.
But this doesn't follow just from the general framework of string field theory?
String field theory gives you the following.
But the string field is equivalent to the existence of worldsheet CFT.
The string field theory will give you that. The string field theory will give you something similar, and especially what we do, let me go back to this, is that on the sphere, we assume that each insertion is surrounded by a hard cutoff box of size epsilon. Okay, so if I do an insertion, suppose this is Z1, suppose this is Z2, and this is Z3. So each insertion comes surrounded by this. So no two insertions can be closer than 2 epsilon. Okay? And if you're familiar with string field theory, this is basically related to the local coordinate charts. But the local coordinate charts, where basically you map it, but with an epsilon cutoff. Usually this is not what string field theory does. But if you specify a local chart with size epsilon, like f of w gives you z, this f of w is like epsilon times w, will give you something similar to that. And in fact, since you asked, these focus on 3 insertions, a sphere with 3 insertions. You know, this gives you what we call in string field theory the fundamental vertex, right? So we build 3-level Feynman diagrams from this. Suppose I want to build this guy from a sphere with 3 insertions. Well, this is going to be the Schwinger parameter. The Schwinger parameter of a sphere with 3 insertions with each box have size epsilon will give you a log epsilon. This is precisely what I had here with the R. So if you want to repeat this calculation, you have to go through this process about this answer, right? You start the sphere, put a local coordinate charts, put a size epsilon, build a 3-level fundamental vertex, you're going to get this. But this is a very arduous way of doing it. It's a very long way, but I guarantee you'll get the same answer. So the origin of the log epsilon is a cutoff on the Euclidean Schwinger propagator of a sphere with 3 insertions, each of size epsilon. That's to answer the question you asked earlier. Precisely. And to answer another question, if I have a Feynman diagram, now the epsilon cutoff will regularize the length of the Schwinger propagator. That Schwinger propagator comes in the 4-point function. I'm out of time, way out of time. Okay.
You can wrap up.
Okay, so the last point I will say is that you might take this as a seed for going off shell, but as you have noticed, I'm not really venturing way off shell from the conformal fixed point. So this prescription as it stands right now doesn't allow me to venture way off shell. So if, for example, if I have a conical singularity, and a conical singularity is to be small. So if beta equals 2 pi, delta is going to be small. Beta 2 pi minus beta is small, really small.
Does it depend on the sign?
Sign, is that the excess or no, it doesn't. It's just going to be small. Excess or deficit. If I want to really venture off shell, which is what we're trying to do now, for example, if we want to prove the RT formula. Like if I want to go to ADS3, go off shell, take ADS3 off shell. So get the cigar, take the cigar, and deform the cigar by some deformations. The cigar will be off shell, or the ADS3 will be off shell. It's going to flow, blah, blah, blah. But then it will be really way off shell. If you want to prove the replica trick in string theory, how do you do the replica trick? Well, the background of the replica trick where you sew points and you glue points along the surfaces is way off shell. You agree? It's not a string theory background.
But
So
you need to take only derivative, right? So
And go
since
to
you-
but that's good. So then there are two ways to go. So let me end with that, because this is an ongoing project now. You need to take you either do it to go, the n goes to 1, which is what we need to basically prove entanglement entropy, not Renyi entropies. And we do Renyi entropies, we really not to go way off shell. It's all right. You either do this using orbifolding. So this is a standard technique, like double car. You go off shell, but then you will have to tell me the analytic continuation. What is the problem? The problem is if I stay on shell and orbifold, right? You have to tell me how you're going to analytically continue from an integer n to real n. And analytic continuation from integer n to real n takes you off shell.
You can't just use Carlson's theorem or whatever.
Well, no, it's not. That's exactly the point. You need to. That's exactly the point of Witten's paper in 2018. He says we're trying to make sense on shell of the analytic continuation. Or, as he mentions in the paper, the other technique is they give you the path integral defined off shell on any off shell background directly. So either I give you the path integral defined on an off shell background, then you don't have to worry about analytic continuation. Or stay on shell, but you have to worry about analytic continuation. So you have to go off shell. There's a lot of examples like this in string theory if we want to make sense of these results. What I'm proposing here is the other way around. I'll give you a technique to go off shell, and in fact, there's a third paper that just happened to be going on in the last 2 weeks, where we found a generalization of this. We found an operator that takes you a finite distance away in RG space, so way off from the conformal field, from the conformal fixed point, way off. A generalization of this, a very beautiful mathematical structure with Alexander Frankel at Stanford. And it takes you away, really, you can define string theory for you away from the conformal fixed points. You can do more things than what just these two can for you. And this is something that's going to be also really soon. So I'll end here.
Okay, let's thank Amr. So I think we had a lot of questions that people might want to leave, but those interested in grilling Amr a bit more can stick around, obviously.
I'm happy to stay here until 9. Yes.
So morally, why is the first point true? Sure. You're saying something like
this one?
This like dd taking derivatives with respect to log of epsilon,
yes.
right? It's equivalent to the Feynman I epsilon description. You're saying somehow, like, how are you? Why is Lagrangian signature encoded in this?
Good.
Yeah.
So this is okay. Maybe I can project now. I have some slides on this. Maybe make it a lot easier because I need to show diagrams. How do I do that? Sorry.
Okay.
Oh. Because this is a beautiful part of the paper, and it's key to what even going to work now. Just click.
No, it's
It's warming up.
warming up.
Okay. And I didn't also get to the gauge orbits, which is the ambiguity part. And this is the new part that when I went to.
Could you turn on your laptop?
What's that again?
Would you turn on your laptop?
Oh, it's off because it's the power. Sorry. Yeah.
How is that?
Let us see. No. It has. It's just. I'll just need to do that. The recording's off.
No, it's
Still on.
everything you said could be used against you.
Okay. In a court of law.
Can and will.
Can and will.
I've never been to court, so I don't know. Is it here?
Okay. There's a couple of things here. The question about the S matrix. Yes, the S matrix, Lorentzian S matrix. Good. Maybe I'll do it here. So this is let's start from here to answer the question. I have a sphere with 4 insertions, and this is a hard disk cutoff. So each insertion has this epsilon. For marginal deformations, for 1,1 deformations, you can do a conformal transformations as long as you're away from the insertions, because there's nothing. The conformal symmetry is only affected near at the insertions, so I can get this sort of thing. It's just to keep that this sort of pants diagram, or where the insertions are 03, 04, 01, 02, and it looks like this. Now, this propagator is a Schwinger time propagator. So let's go to quantum field theory. Even in quantum field theory, even for string theory, that's called the word line formulation of string theory, which is the closest thing if you want to string theory. In this case, we express this propagator with let me write this before I step here. Just a step, one step. So usually the Euclidean Schwinger propagator looks like this. L0 minus L, this is the level matching condition. And usually it looks like this, right? 0 to infinity, and I have the S, and I have e to the minus S times L0 plus L0 bar. This is closed string theory. Well, minus 2, and this is equal 1 over L0 plus L0 minus 2. P squared plus n squared. This is a Schwinger propagator, Euclidean Schwinger propagator. And if you have a world, so on the world sheet, suppose you're near a pole. Suppose you're really near. So you have a 4-point function, and here this p squared plus n squared. Usually a off shell. Usually it's not automatically on shell. But now you're very close to being on shell. Very close to the point where p squared plus n squared is equal to 0. The near pole. What does this mean? This means this. Let me draw. This means you have a sheet. You have a world sheet with this long neck called a degenerating world sheet. It's called this is called a. Let's assume this is a sphere. Could be any genus. And when you're near a pole, the world sheet degenerates. It's called a degeneration. It develops this long propagating tube. And this long tube is parametrized by S, has a parameter S. But if it's a closed string theory, it also has parameter alpha, which is the angle, right? Good. So this is for closed string theory. Now, so if you have a world sheet near degeneration, near a pole, the log epsilon, the UV cutoff on the world sheet, regulates everything. It regulates that length. This length from this equation goes to infinity. So this is infinite. So what does this mean? When I have a pole, I have an infinitely long Schwinger line, Schwinger tube. Infinitely long. But now I have a cutoff on the sphere. So this cutoff, what it will do is it will put a log epsilon divergence on it. So it make it log divergent. This log divergence, log epsilon. And so I'll have a formula that looks like this. This is what? I regulate a regulated Schwinger tube. So instead of this tube going to infinity, it will be cut off at certain point. And this is proportional to log epsilon. Does that make sense? So instead of it going to infinity, this is what we may regulating a pole instead of because a pole means infinite, means something infinity, because in here, this is 0. Okay. Now here's the key thing. Let's take a look at the Lorentzian time Schwinger propagator that was written by Witten. Thank you so much. Meeting being recorded. I still.
Oh, it's
Should I leave?
no, it's like it got disconnected. I think your laptop got fall asleep.
Oh, sorry. Yeah, that's my fault. So now this is the form, the Lorentzian form of this. This Lorentzian form takes almost the same thing, except that here also I have what we call a regulating divergence. This thing regulates the oscillations because this is an I. So for p squared plus m squared not equal to 0, if you're not near a pole, there'll be a very, very violent oscillations, and we put this regulating factor to regulate the oscillations because of the I factor, because of the complex factor. This is the Lorentzian time Schwinger parameter version of this. And it looks like this, as suggested by, looks like what? Looks like field theory. P squared plus m squared minus I epsilon. So I go a little bit away from that. Now, what we found in the paper is the following. So let's suppose this is the prescription given by Witten. Suppose I take the metric on the world sheet is Euclidean except at near degeneration. So this is the prescription just proposed by Witten. I take S is my Euclidean, and then near degeneration, only near a pole, I take it to be IS in the imaginary direction. So this is a contour that was proposed. So take everything to be Euclidean except near degeneration, aka near a pole, then venture into the complex and take it to IS. And then he shows in the paper why this is true, and this is related to something called the complexification of the moduli space. That's basically the punchline. But take a look here, what we're doing. What we're saying is that I can write the Lorentzian Schwinger time propagator. Look at this in terms of the regulated propagator. If I consider the length of the tube to be imaginary. Think about this for a moment. Let this sink in for a moment. So I integrate over a distribution of complex tubes. So
there you want t equal to that, or you want curly epsilon to be?
No, this I minus I log.
T is in the integral. So
yeah, so I'm integrating over this.
Epsilon. Okay,
yeah, that's exactly the point. Is that I'm taking the Lorentzian Schwinger time over my tubes. So when I go in the imaginary direction, I imagine I have tubes of length log epsilon all the way up in the imaginary direction. And then we show that this is the S matrix of genus 0. This is the notation of n insertions as a function of the Feynman I epsilon is equal to the d of t. This is the Schwinger time. And this is the regulating factor. And this is A0n. So give me the amplitude, the S matrix amplitude. This is on shell, S matrix amplitude as a function of the UV cutoff of the UV cutoff, not the Feynman epsilon cutoff, just the regular epsilon. Apply this, I'll give you the S matrix in Lorentzian time. And we show this explicitly how it works in the paper. By integrating over a distribution of logarithmic divergences. And we show that for each pole, what should we get? So if you're sitting on a pole, right on a pole, each del by del log epsilon prescription will give you this factor. 1 over, or I actually, 1 over Q, which is the transferred momentum, minus I epsilon. So for each pole, you actually get that factor. And it's kind of beautiful, it works. And this makes sense because it has to do with something called what Witten calls in the paper, you complexify the moduli space. Why does it call the moduli space? Because the tube is a modular parameter. The tube is a modular parameter, and so we basically complexify it. And so we're able to make sense of this in the S matrix regime. If you have time, then I'll get you the gauge orbits. That's the way. Because it is the most beautiful part, I think, that people like, and which I did not mention, which has to do with the ambiguity. It's called the gauge orbits. In essence, SL to C is not a number. It is completely wrong to deal with the SL to C as a number like you deal with the SL to R. It's not a number, it's a lot of numbers. And the way we deal with it is in the DF proposed sense.
Didn't the Lorentz, Eberhardt, and everybody other?
Yes.
They studied
Yes.
this.
And not on the disk.
Yeah.
On the disk.
On the disk.
Not on the sphere. They did not know how to handle the sphere. We know how to handle the sphere now. And it is, the point is, people look at the SL to R as a number. That you'll say, tell me, what is that number? That's why it's ambiguous. But we deal with it as a multiple numbers, right? And instead of dividing by a number, we mod out. Now there's a sense of modding out by equivalence classes and the sphere. So let me go take you, because it's kind of, well, okay. The look on your face, okay, fine. I'm
happy
you
to
can
hear
sort of, I need to go do something.
When are we going to dinner?
Yeah, I need to go do something, so let's meet over there next to the elevators maybe, or next to Tim's office, anywhere on the 9th floor, at like 5:50, say?
5:50, so in like
15 minutes?
15 minutes, okay. 15 minutes, okay.
Where are you going for dinner?
We haven't selected a place yet. I was hoping to get recommendations from you guys.
Okay.
But you're planning to go at 5:50?
Well, just meet by the elevators or there by the kitchen at 5:50, and then we can decide.
Okay.
Okay, near Tim's office.
Say that again? Yeah, let's say near Tim's office.
Okay.
The fact is, because I also need to do stuff, but it's, since you asked, this is basically how we deal with it in this question in the paper, is this. Let me, not this one, probably this one. Yeah, there's some figure. This is what a degeneration looks like. Here, let me show you. Yeah, this is the calculation of this thing, of the action. But yes. So suppose I start with a sphere that looks like this. I define the pre-moduli space. Pre-moduli space, because I haven't fixed any points on the moduli space here. So I define the pre-moduli space as the space of all possible insertions of vertex operators as Pm0n. Then if I mod out by SL2C, I get N0n. I get the moduli space on the sphere with n insertions, okay, which has this dimension. But now I want to regulate this with a cutoff. So now what do I get? A notion of the following. Now I'm going to modulate it by epsilon so that I define another moduli space, a regulated pre-moduli space. The regulated pre-moduli space satisfies the condition that no two operator insertions are closer than 2 epsilon on the sphere. So basically, you're not allowed to insert at any point. No. Okay. You're taken off in the moduli space. Good. So now, with conformal invariance, because we're dealing with 1,1 insertions, conformal invariance guarantees that the CFT amplitude density is invariant under SL2C, action on all points simultaneously. This is true. But the regulated pre-moduli space is not. Non-invariant under SL2C at all. It's broken. But the observation is any two elements on the pre-moduli space can lie on the same orbit. And you can find an SLTC transformation or related by them if they lie on the same orbit. And that's guaranteed to happen. So if you have 4, Z1, Z2, Z3, Z3, and they're both 2 epsilon apart or greater, I can find an SLTC transformation that will take me from Z3 to Z4 and Z1 to Z2. So I have equivalence classes on the sphere. Now, act on the regulated moduli space with SL2C. What you get is a regulated moduli space. Good. So if you have a regulated moduli space, call the elements of the moduli space gauge orbits or equivalence classes. Now, let us compute. Now, here is the question. Do we divide or quotient out? Now it's becoming similar to like that integral Fourier-Popov sense. The volume of each omega is different. The volume of each gauge orbit, where 2 points lie on the same, is different because it is going to be different by the number of insertions. So suppose I have 10 insertions and 5 insertions, that volume will be different. Also, it depends on the cross ratio. Of course. Right? Good. Therefore, dividing, but because of what I said, is not. What are you dividing by? By the volume. This should be volume of omega, sorry. This would be volume of omega. What are we dividing by? Which number? So then, a priori, I show you that divide is not the right thing. But then, what you could do, before I show you what we do here, is that you can compute the volume of omega for each equivalence class, and then divide inside the integrand. So before you pull it out, you divide by volume of omega 1, omega 2. You do this for all gauge orbits, and good luck doing that. Or do this. The only is modding out. So you think of it as modding out equivalence classes. So basically, just as like something like what we do in Fourier-Popov, some sort of, except that when we factor out the integral over the orbits, here we say just divide by it, because it's a one number and it's an infinite number. It's an infinite number, but it's one number. Here, let's get more closely. The divergence in L2C comes from H3. So it's a hyperbolic manifold. Good. Now, the cutoff is invariant under SU2. That's good. So take H3 to be the hyperbolic 3 manifold with unit curvature radius. Pick a point P in polar coordinates, and which is the origin. Good. Now take a point and shoot a ray out of that point. So shoot a geodesic and follow that geodesic. That geodesic is parameterized by a ray or whatever we call it. It's parameterized by lambda from one direction in P. So because P could go in any direction. And compute the solid angle from that P. So fix a point, take a ray, compute the solid angle, and you'll find this. This you can do for any gauge orbit. So pick omega, pick anything. Pick any gauge orbit, pick a point P, you'll find this thing. For any gauge orbit you choose, for any P you choose, for any ray out of P you choose, you will find that always the non-universal data is not in the log epsilon. Log epsilon will always, for any gauge orbit omega you pick, and for any point P you pick to be the origin, for any ray out of P you pick, you're always going to get a half. You're never going to get any of the A and B parameters which depend on the choice of the conformal frame, the choice in the origin P, and the choice of the ray.
Yeah, that's what I meant.
Then, if I do that for any omega, just act by T2, the one that cancels epsilon minus 2. And what you get is a factor that's proportional to 1, but not AB. So this 1 is true, it's a constant that we did not calculate, but it's going to be always the same constant for whatever gauge orbit you choose. Then, if this is the case, then really the effect of acting with T2 is modding out by this gauge symmetry. And that is exactly how we should think of SL2C. The problem of ambiguity is because you want to think of it in terms of SL2R, which is a number. But what is the volume of SL2R? The volume of SL2R is, after you cut this guy, is minus pi squared. But that's a definite number. What I just showed you is that I cannot deal with the volume of SL2C in the same way I deal with SL2R, and that's why the derivative is different than the division. Because if I don't take the derivative, I just take the division, I'll be left with a lot of junk. So that's the reason why. Yeah, that's to answer some of the questions. Anyway.
You mentioned in the end you have some procedure, some kind of transition of T2 that allow you to go far away from the fixed point. What do you mean?
I mean this. So in the
can you illustrate this procedure just for the simplest RG, like from Ising to the gap phase?
Well, I don't have an example now, but I have a proof of that if it should work if I apply it on some example. So let me show you one slide on this.
But it won't work for that particular.
It will work. Right? It should work and it will work. So we haven't tested it yet because this is
what observable is this?
So let me show you. Well, let me show you something first of all before I get to that. So when you go off shell, let me back up just one. This is the equations of motion section that we said we do. Suppose when you go off shell, you have terms like this that you want to eliminate. Sorry, there's a lot of details that I've, yeah. When you go off shell, you have terms like this you want to eliminate basically, which is these terms. Yes, so let me point out. These are called, these terms are called spurious tadpoles, and because they depend only on the worldsheet metric. So, for example, the tachyon tadpole, T0, this will be epsilon, for P equals 0, P is just an integer, this will be the tachyon, and we'll have epsilon to minus 2. But if you want to go off shell even more and more, then you need to be able to cancel the effects of this when you go back on shell. So R to the P. So what T1 and T2 can handle is that T0 cancels the tachyon tadpole, T2 cancels the tachyon and the dilaton tadpole, T1 cancels only the dilaton tadpole. So I want to, these are called non-minimal couplings.
These are just the structure of the divergence which you can infer from the counter terms.
Yeah, but when you go off shell, exactly. So the point is when you go off shell, these things are there and are allowed as terms on the worldsheet. But of course, when you should have a prescription that deals with the poles coming from there, because you do not want your action to depend on this at the very end when you go back on shell. You don't want that. In the sense that, so here.
So you have a higher more derivatives.
Yes. So these we can only handle up to R, and relevant and irrelevant deformation. So this is what exactly we can handle, or these T1 we can handle. And then what we do is that we cannot handle anything T1 can, T2 cannot. And so we put some window on the deformations around the CFT. We put some and renormalizability condition, which basically means that the conformal dimension of the deformations away from the CFT have to be bounded by these limits.
N is the number of, N is, sorry, what is
N is the perturbation theory, so number of insertions, or the order in perturbation theory. So you can see, these are conformal dimensions of the perturbations. So if I deform away from the CFT, I'm not allowed. T2 limits this, and you notice that, let's take it n equals 1. N equals 1, this means less than 4. Because if I have less than 4, this basically means r squared. So I cannot handle dimension 4. Then there'll be poles and there'll be off-shell stuff that T2 cannot cancel and eliminate. And T1 is even worse. But we show that within this window, they give consistent results. Now, if I want to go off-shell, way off-shell, I need to eliminate the renormalization window. I need to be able to deal with descendants, because also descendants begin at 4. So here it is. So for example, suppose I give you a prescription that looks like this. T3. T3 will eliminate epsilon to the -2, epsilon to the 0, but it will also eliminate epsilon to the 2. Correct? Just continuing the T1 and T2. Good. So with this observation, it turns out we have this beautiful structure. This is not in these 2 papers, this is a 3rd paper. That it turns out that if that this sum is related to the sign function of a del by the log epsilon prescription. This is something by Euler, that you can express a sign of a number as a product of the roots. So then what you do is like this. T of sign is going to be, so this operator sign of del by the log epsilon is going to be sum over all, that's why I call it the infinity. And it gives you exactly the monodromy around epsilon goes to 0. So the beautiful structure that comes out of this is that you imagine your cutoff as being complex, and you only get a non-zero answer if you get non-analytic behavior. Basically, it's a monodromy operator. It takes you around epsilon goes to 0 in the imaginary space, and if the monodromy is not 0, it gives you that universal answer, and you can see it beautifully here. So this is a monodromy operator, and this is way off shell, and it gives you as a matter of fact, this is an eigenvalue, and this is a generalized eigenvalue. So there's a beautiful structure lying here, and this one.
What is the physical significance of the object that you get from acting this operator on the boundary function?
The physical effect is eliminating poles. So, for example.
Yeah, so it means it's
the imaginary part of the amplitude when you continue to the to the Lorentzian time, to the imaginary part of the correlators.
So that is exactly why we're going to use this that observation to claim that now we can construct off-shell actions in Lorentzian backgrounds. Because as I showed you, the T1 and T2 know about the
we can continue.
No, okay.
We can continue at the
somebody's waiting. How long?
No, it's like 5.
Oh yeah. So yes.
I needed to do something even before that. So see, I can go on forever.
Yeah. Thanks for the explanation.
Of course, anytime.